Everyone. So this is the first lecture on sampling distribution. As in the previous, that was our overview lecture. So in that lecture, I told you about the contents of the sampling distribution, and we will start from the Chebychevs inequality. So Chebychevs inequality. Chebychevs inequality. And And why we study this Chebychevs inequality? Because the other inequalities, let it be Cauchy-Schwarz inequality, let it be Frenchet's inequality. So those inequalities are only for expectations. And this Chebychevs inequality will give us the upper bound and the lower bound of a probability. Remember this, it gives us the bounds, that's lower bound and upper bound. So basically Chebychevs inequality gives us bounds, whether it be lower bound or upper bound of what? Of a probability. Whenever we are not given with the exact distribution, we can use the Chebychevs inequality if only we have the finite mean or finite variance. So this Chebychevs inequality is only valid when mean and variance or mean or variances are finite. Clear? So what's Chebychevs inequality? So this inequality basically gives us the bound. That's the upper bound or lower bound of a probability. Right? And this Chebychevs inequality, why I started this Chebychevs inequality? This is not the part of sampling distribution. This is simply an inequality. Why I started this? Because this Chebychevs inequality will be helpful in proving the weak law of large numbers, convergence in probability as well, and to show that an estimator is a consistent estimator, we can use Chebychevs inequality as well in those cases, right? If variances or mean is infinite, we cannot use Chebychevs inequality. When mean and variances are infinite, Chebychevs inequality is invalid. Right? So let's come to the statement of this Chebychevs inequality. Chebychevs inequality statement. The statement is let the random variable, we have a random variable x. Already you know what's a random variable. Random variable is a function that takes specific values, right? So let random variable x have a distribution of probability about which we assume only there is a finite mean and finite variance, which means that expectation of x should exist and variance of x should also exist, or we can say which is less than infinity. which is less than infinity, that is the finite. Then for every k is some number, for every k, so this probability mod of x minus mu greater or equal to k sigma less or equal to 1 upon k square will give us the upper bound, So this mu is mean, that's expectation of x, this x. So whenever we take expectation of this x, so that's mu, which is greater or equal to k sigma. Sigma is not deviation, and k is some number which is less or equal to 1 upon k square. K is some constant, right? K is some constant. So, and the value, remember, and the value of k is always greater than 0, or in some cases it should be uh, greater than 1 also. It should be greater than 1 also. Now, 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 for the lower bound, we have probability x minus mu, which is less than k sigma, which is greater or equal to 1 minus 1 upon k square. So this will give us lower bound. This will give us lower bound. So remember here, upper bound plus lower bound should be equal to 1. Remember this. From this, upper bound and lower bound should be equal to 1. Right? This Chebychevs inequality is useful for both continuous random variable as well as discrete random variable. So what I say, this Chebychevs inequality is useful for both continuous random variable as well as discrete random variable. So this Chebychevs inequality has some other forms. Let's write them. C probability x minus mu greater than c, which is less than or equal to variance of x divided by c square. This will give us upper bound. See, the difference is whenever we take only some constant c, the inequality changes into variance of x divided by c square. This c square, and this is variance of this random variable x, right? This random variable x. And the other form is probability mod of x minus mu, which is less than c. This is greater than 1 minus variance of x upon c square. This will give us lower bound. So this is the other form of Chebychevs inequality, right? So this was the statement of Chebychevs inequality, that we have a random variable x, which has a distribution of a probability about which we assume that only there is a finite mean and variance. Then expectation of x should be existed. That's expectation of x, finite mean and finite variance. So this is the statement. So see, now let's move ahead. Then we have another inequality in this, that's Markovs inequality. Which states that let g of x be non-negative function of a random variable x, then for every k greater than 0, then we have what we have? Probability of some function, that's g of x, which is a non-negative function, greater or equal to some k, which is less or equal to expectation of g of x upon k, not k square. Remember, this is here in the denominator, there is only k, right? So if we have like this is less than k, then this is equal to 1 minus expectation of g of x divided by k. So these are my two forms of Markovs inequality, right? So so here is important note here, let g of x is equal to mod x raised power r, then probability mod of x r greater or equal to kr. See, mod of x r raised power r greater or equal to kr, that will be less or equal to expectation of mod of x r divided by kr. Remember this. So now let's look at some examples on the basis of Markovs and Chebychevs inequality. So question is like this: if we have some MGF, that's mxt is equal to 1 upon 1 minus 4t raised power 5 and t is less than 1 by 4, then find probability x is less than 40. Use Markovs as well as Chebychevs inequality. Markovs and Chebychevs inequality. To see, let's analyze the MGF first. See, mxt is equal to 1 upon 1 minus 4t raised power 5. So we can write this as 1 minus 4t raised power minus 5. So this is some MGF of gamma distribution with parameter alpha is 5 and beta is 4. Alpha is 5 and beta is 4. If MGF is like this, 1 upon 1 minus 1 by 4 t raised power 5. So this is the MGF of gamma with parameter 5 comma 1 by 4. So only the parameter, this changes, beta changes here, right? So this is alpha, and with this variable t, we have the constant value, that is the value of beta. So this is the value of beta, this is the value of beta, and this is the value of alpha, this is the value of alpha. Remember this. So what's expectation of x from this? What is the expectation of from this? See, you can, if you don't know the MGF of any function, so you can also do one thing, just differentiate this function. So you will get the MGA expectation. So what's expectation of x? This is d by dx of mxt. So that is minus 5, 1 minus 4t multiply internal differentiation of this, that's minus 4, right? So this is minus 20, 1 minus 4t at t is equal to 0. This will give us the expectation, that is equal to, this is minus minus plus 20, that is 20, right? So this is the one method. If you don't know the MGF of which distribution it is, then you can directly do expectation of x by differentiating the MGF only, right? So see what will I do? Wait a minute. Uh, what will I do? Say, say, see, expectation of x is equal to d partially differentiate with respect to x of this MGF, you will get the expectation of x. And what's expectation of x square? That is d by dx square m dash xt. Or we can see, you can see not square here, you can see this is the second derivative of this. And then you know variance of x is equal to expectation of x square minus expectation of x whole square. From here you can get the value of expectation of x, expectation of x square, expected variance of x. See, this is the MGF of gamma. Alpha is 5, beta is 4. So expectation of x would be 5 into 4, that is 20. Variance of x is alpha beta square, that's this. This is equal to 80. Now let's calculate the probability, that's x is less than 20, which is equal to expectation of x divided by 40. This is 40, this is 40 expectation of x divided by 40, which is equal to, what's expectation of x? This is 20 upon 40, that's equal to 1 by 2. So by Markovs we get probability x less than 40 is equal to this, right? So now by Chebychevs probability x is less than 40, that is by Chebychevs it says that probability, let's see, probability is x greater than 0 less than 40. So probability 0 minus 20, as we subtract the mean, so this is x minus 20 is 20, 40 minus 20 is 20. So we can write this as probability mod of x minus 20 is less than 20. Mod of x minus 20 is less than 20, and this is equal to 11 whenever we have the less than sign here. So this is equal to greater or equal to 1 minus variance of x upon this k square, this is 20 square, that is equal to greater or equal to 1 minus, what's variance of x? This is 80 upon 400. So this is equal to 400 minus 80 upon 400, which is equal to 320 upon 400. This and this goes, so this is equal to 2 16s are 2 20s are 2 8s are 2 10s are 2 4s are 2 5s are. So this is the answer, right? This is the answer. Now let's do another question. That is question is like this: a symmetric die is thrown 600 times. Find the lower bound for the probability of getting 80 to 126s. So see, as the question is asking about the find the probability of that number of sixes is between this and this, right? So we need to calculate the value of this. So here, as you know, whenever we have a die, the probability of success is 1 by 6, right? So here n is equal to 600. Now find the lower bound. we are calculating the lower bound. So what's the mean of this? Or we can simply from this you can say x follows binomial 600 comma 1 by 6. So expectation of x is equal to 600 into 1 by 6, as this is equal to NP, as you remember from the discrete distribution. That's a binomial distribution. So this is equal to 100. So expectation of x is 100. So what's variance of x? This is 600 into 5 upon 6 into 1 by 6. That's NQP or NPQ. So variance of x is equal to 500 upon 6. Now subtract the mean from left hand side as well as right hand side of the inequality. So probability 80 minus 100 is less than x minus 100 is less than 120 minus 100. So this is equal to probability minus 20 less than x less than 100, that is 20, which is equal to probability mod of x minus 100 is less than 20. Now we need to calculate this. That's the lower bound. That's the lower bound, and this is equal to, this is greater or equal to 1 minus variance of x upon epsilon square. So this is my epsilon square or k square, you can say. So this is equal to greater or equal to 1 minus what's variance of x? This is 500 divided by 6 into 400. So this and this goes. So this will become 1 minus 5 upon 24. So which is equal to 19 upon 24 is my answer of this question. I hope you guys understood the whole concept of Chebychevs and Markovs inequality very clearly, right? So let's move ahead. Let's see one of the interesting question. That's the mix of the MGF and Chebychevs or Markovs. See what's the question. Question is, let x be a random variable with MGF mxt, where t is from minus h to h, then which of the following is true? Which of the following is true? So number one is probability x is greater or equal to a, which is less than mxt. Second, probability x is less or equal to a, which is greater than e minus at plus t mxt. Probability x is greater or equal to a, which is less than e minus at mxt. Or D, that's none. So let's give a try on this question. So you know about the MGF, you know about the Markovs inequality. So here is the use of the Markovs inequality. So what is Markovs inequality? That's probability x is greater or equal to a, which is less than expectation of x divided by a. So simply we can do here, see how we can manipulate this into this. So see, this is probability, multiply both sides by t. So this is tx, which is greater or equal to 80, right? So this is probability etx is less or equal to, this is probability etx, which is less or equal to e80, not less or equal to, this is greater or equal to. So we are just making this exponent, this is greater or equal to. So see, this is equal to expectation of this, expectation of etx divided by this, divided by this. So this is EAT. So this is E minus AT. Expectation of ATX is the MGF MXT. I hope you remember this and you understood this very well, because this is the MGF. So whenever we say this is equal to expectation of ETX, then whether it's discrete or continuous, that is the secondary question. If this is discrete, we write this expectation of ETX probability of X, this expectation of ETX f of XX. So this is the MGF, right? So here expectation of ETX is the MXT, right? So this was all about the Markovs and Chebychevs inequality. I hope you guys have understood this very well, and let's subscribe to my channel and share this video. And I'm going to upload some new videos on the other topics of the sampling distribution. Uh, and in previous lecture I have already discussed about what we are going to uh, learn in this core sampling distribution till testing of hypothesis, right? So thank you.